All right, guys. So we'll also discuss question number 19 in exercise 4C. Okay, so they say an aircraft of mass 2 tons flies at 400 km per hour on a path which follows a horizontal circular arc in order to change course from a bearing of 60 degree to a bearing of 15 degrees. It takes 25 seconds to change course with the aircraft banged at angle alpha to the horizon. Calculate the two possible values of alpha to the nearest degree and the corresponding values of the magnitude of the lift force perpendicular to the surface of the aircraft's wings. Okay. So guys, in order to do this question, there are several things that you need to know. Okay, so the first thing is you need to understand how to draw the force diagram. Okay, so basically when they tell you that, I mean, when it comes to horizontal circular motion, okay, so this is a horizontal circular motion sum, there are normally only two things to do, right? We always have vertical equilibrium. The object will always be in vertical equilibrium, and also the object will, you'll always have to use F equal ma towards the center. All right, so here they say this particular aircraft, it follows a horizontal circular arc. Can you see? So that's where you have the circular motion, and it's following this circular arc to change the course from a bearing of 60 to a bearing of 15. So it's only following the circular path only for this point from 60 degree to 15 degrees. So that's the path where it follows the circular motion. All right. Okay, so that's one thing you need to know. And the other thing is, okay, in order to do this properly, you need to be able to mark all the forces. All right, guys. So over here, so you can see over here things that you need to know here. Okay, so in normal flight, the lift force. So basically, in a flight, we always say there is something called the lift force. Okay, so this is what I mean, you need to. Okay, so the lift force is actually what balances the weight, isn't it? So obviously, the weight is acting vertically down, and normally, if you are not, considering without the bank, if you just take the flight in its normal state, the weight acts vertically downwards and the lift force is acting vertically upwards, balancing the weight. All right, so that's how we have the vertical equilibrium. Okay, but now over here by banking, okay, so since we are banking the aircraft, so you can see now the aircraft is not in the horizontal state, it's slightly banked. So one wing is lower, the other wing is higher. So this is called banking, right? So but by banking the aircraft, the lift force is now doing two things. So over here you can see the lift force is actually, you can see it's always acting perpendicular to the aircraft. So you can see the lift force here, this P, what we marked over here is our lift force. So this is acting perpendicular to the aircraft. So when it is banked, it is still acting perpendicular. Okay, so now the lift force is doing two things. Basically, where you're going to take the component. So you can take the component, and they say the vertical component is balancing the weight. Guys, can you see the vertical component? So over here, the T cos alpha. Now you can see the lift force is acting upwards. So when you take the component, you should be able to see that T cos alpha is acting upwards, right? Because this is when you resolve, T cos alpha is acting upwards. Instead of marking it over here, I'll mark it up. T cos alpha acts upwards, and you can see T sine alpha is acting like this, right? This is T sine alpha. Okay, so T cos alpha is now what's going to balance the weight. Okay. Okay, so T cos alpha is now what balances the weight. The vertical component is balancing the weight, and the horizontal component is the force which causes the acceleration towards the center of the circular arc. Okay, so can you see? So these are the important things you need to know here. Okay, so T cos alpha is what you have for the vertical equilibrium along with the 2000 G here. Okay, so mass is 2 tons. 2 tons means 2000 kilograms. 2000 kilograms to when you convert to weight, it's 2000 G newtons, right? Okay, so then and T sine alpha is what's going to be the force that's acting towards the center of the circle. All right. Okay, so now let's try to solve the equation and let's try to find the two possible values of alpha. Okay, all right, guys. So over here, just before we start this one, just one more thing. Okay, what about this path? Now they say this particular plane, it follows a horizontal circular arc in order to change course. Okay, so from a bearing of 60 degrees, so you guys, bearings are measured from the north. So from the north, the plane is currently at a bearing of 60 degrees. So from 60, it's turning to a bearing of 15. So guys, can you see what's going on? The plane is going to bank itself and it's going to travel in this circular path, in this circular arc from this point to this point. So after reaching this point, the plane will just continue on this path. Do you see? The plane will just continue after turning. It doesn't go, I mean, you don't need to go through the whole path, right? I hope you guys understand what's happening here. So previously the plane was traveling in this path. Can you see? So the plane was traveling in this path, and after coming to this point, it decides it wants to it wants to change its course. So to change the course, it banks. So this is the banking diagram, okay? It banks the plane is banked, and then it turns from an angle from a 6-degree bearing until it comes to a bearing of 15 degrees. And then after reaching that point, it goes in that path. Do you understand? So that's what's going on here. So over here, this small path from this point to this point, this path that I'm coloring, this is the path where you have the circular motion. And that is the path that we are interested in. This force diagram is completely concerning that part. Are you with me? It's completely concerning this small part over here. All right, so what we'll do here is you don't need to have all of these diagrams. All you need to do here is, okay, so to apply the two equations, first thing we need to know here is we need to know the speed. Basically, we have 400 kilometer per hour, which we need to convert to meters per second. So 400 kilometer per hour in 1 hour. So 400 kilometer, 400 into 1000 meter, 1 hour is 60 minutes into 60 seconds. So this gives me how much? 1000 over 9 meters per second. Okay, so this gives me 1000 over 9 meter per second, the speed. So let's keep it in exact form at this point. All right. Okay, and then the next thing we can do here is from this course, okay, from the course that they have given you, we can actually use it to find the radius of our circular motion. This small part where you are traveling in circular motion, we need to find the radius of this path. So to find the radius of this path, we can use the help of this particular diagram here. Okay, so how do we do that? All right, so guys, over here, one more thing, okay, actually about this course, the changing course. Okay, I think they're asking you to calculate two possible values of alpha, right? So the way we actually get two possible values of alpha is actually the direction. Now over here, I hope you guys can see. Now I've just taken it traveling from 60 to 15 directly in the shortest way, right? So actually the change, this angle, the changing angle here, this theta degree, okay, could be either way. What do I mean by either way? Now here I've taken it from here to here. Okay, but also the depending on the direction the plane is traveling, this change could even be happening the other way. Okay, this could even be happening the other way. Okay, so basically over here, the plane is over here and it wants to change from 6 degree to 15 degrees. So actually we don't know in which direction the plane is traveling from. So if it is traveling in like a direction like this, okay, if it was coming from somewhere over here, okay, and then it wants to, it wants to change its course to 15 degrees. So if it's coming like this, it needs to go through this entire path to adjust itself to the 15-degree path. Guys, can you see? So actually there are two possible ways depending on the direction. This, there are two possible theta angles. Now, what do I mean by the theta angle? The theta angle is the angle, the angle that the plane is actually turning. Okay, so there are two possible theta angles. So what's the theta angle the plane can turn? There are two possible. Okay, there are two possible angles of turning. Okay, so the first possible angle of turning theta is how much? Okay, so first one is what the one I originally drew from 60 degree. We assume the plane is coming from this direction and it turns until it comes to 15. So the angle change is 60 degree minus 15 degree, which is a 45 degree. So then it only turns, it only goes to the circular path for a 45-degree angle. It follows the circular arc for a 45-degree angle. But also we have another way of doing this. What's the other way? We can, I mean, since we don't know the direction that the plane is where it actually starts from, so you could think that the plane actually starts from this direction. You know, it came originally, it was here, and then it wanted to change from 60 degree to 50. So it has to go through this entire path. Do you see? So this entire, from here to here, it needs to change. Do you see? The second, this is the first theta angle. The second one is from the 60 degree, it needs to come over here. Can you see the full angle? So you need to, this is the angle the plane needs to turn to come from this point to this point. Okay, so then what's the other angle? Can I know the second angle? How do you calculate it? All right, guys. So depending on the direction, it's theta 2. So actually the second angle is going to be what? From 360, the big angle, the complete angle, you should subtract what? The first angle, right? Hope you guys can see it's this small, it's this angle that you need to subtract, right? It's this theta 1 angle that you need to subtract so that you can get the angle the plane completely needs to travel in circular motion to reach this particular bearing. Okay, so 360 minus 45, so which is 315. So guys, can you see we have two possible values for theta. Okay, so now for each possible theta value, let's try to find the alpha. Okay, so let's first consider when theta is 45 degrees. All right, guys. So when theta is 45 degrees, let's try to find, okay, let's try to get the arc length. Okay, so if theta is 45 degrees, we are going to travel in this yellow part, the brown part that I have drawn here. Okay. Okay, so let's get the arc length. Okay, guys. So we know we can get the length, basically the length, the arc length of this particular sector, or the distance the plane. Basically, in other words, it's the distance the plane is traveling, right? Because the arc length gives you the distance the plane is traveling in the circular path. So arc length is angle over 360, right? I mean, because it's in degrees. Okay, I'm doing this in degree mode. You can't use arc length as r theta here because your theta is in degrees. Theta is, if your theta is in radians, you could have gone for r theta. Okay, so because it's in degrees, I'll go with 45 over 360 into 2 pi r. So this is basically grade 10 maths, grade 9 math, right? Angle over 360 into 2 pi r. Okay, so I think all of you agree that it's the distance the plane travels in the circular path. Do you agree? This can also be found by the now normally, you know, you can also find the distance the plane travels by using what? Guys, you know, speed equals distance over time, right? You guys know that speed equals distance over time. So if speed equals distance over time, distance is equal to speed into time, right? Speed into time is distance. Agreed? So basically, I can get the distance that the plane travels because I have the speed of the plane. So it's 1000 over 9 meters per second. 1000 over 9 meters per second into the time means, guys, we have the time duration the plane travels in the circular path. It takes 25 seconds to change course. So this is 25, guys. So we have 25 seconds here, and you can see the units match, and we have an answer here in meters. So I hope you guys can understand that both sides of the equation gives you a distance, isn't it? So this gives you the length of the circular path. The length of the circular path, in other words, is the distance the plane is traveling, right, over in the circular path. So this is what I have over here. And from this equation, you can now calculate the radius. Okay, so you can calculate the radius. Let's get the value of the radius. 1000 into 25, the 360 goes up. 1000 into 25 into 360. I have 9, 45, and 2 pi coming in the denominator, right? 1025, 360, 9, 45. Yeah. So this is all you need to type in the cal, and you can get the value of the radius. Let's get the r value. All right, guys. So we have the radius of the circular path the plane travels if it's turning through an angle of 45 degrees. Okay. So now how do we go for the alpha? Okay. So now this is where we are actually going to use the circular motion now. So now this is the time we are actually going to use the help of the circular motion. So what we can do here is we can apply F equal ma towards the center, and also we can apply vertical equilibrium, right? So basically over here, if you consider vertical equilibrium, okay, so you can see my force diagram is complete here. Now this is the diagram of the plane during the circular part, okay? So what do we have here? So we have here T cos alpha is equal to 2000 G, right? T cos alpha is equal to 2000 G. Now over here, alpha is the banking angle, okay? So don't confuse that with the circular motion. Now circular motion is something else, okay? The plane is banked while traveling in the circular motion, okay? Now we are going to consider the individual forces on the plane. So T cos alpha equal 2000 G to keep the plane in vertical equilibrium. You can see I do not know the alpha, I do not know T. Okay, so then what's the next option? We apply F equal ma towards center. F equal ma towards center. So what are the centripetal forces here? Centripetal force is T sine alpha. I marked at the very beginning, right? It's T sine alpha, nothing else, right? We only have T sine alpha. It's a centripetal force. Mass is 2000 kilograms. Acceleration, we can use r omega square or v square over r. So this is the acceleration. The double arrow means the acceleration, okay? So here the centripetal acceleration v square over r should be good, right? Is that okay, guys? Okay, and I think you can see we know both the values. I mean, we know all the values here, right? I mean, T sine alpha 2000 over, shall I put the radius at the denominator? 2000 into radius is 1 over 3536.776513. I'm just using the full value. You can put the answer from the cal into v square. So v is 1000 over 9. So 1000 over 9 square. Okay, guys. So at this point, just don't go to type it in the cal at this point. I just want to find the alpha value. How do I get alpha? This is equation 1, this is equation 2. To get alpha, we can go take equation 2 and divide by the first equation, right? So second equation divide by the first equation. Is that okay? I think second equation, shall I use this? This is easier. Let's use this and divide. Okay, look, it becomes easier then. Otherwise, it's taking too much time. So T sine alpha, second equation, divide by the first equation, T cos alpha. Second equation, T sine alpha on the right side, 2000 into V square over R divided by 2000 G. Guys, can you see? It becomes easy to use. Just use this for now and we'll substitute later. 2000 cancels out. T cancels out here. Sine alpha over cos alpha is tan alpha. And you get here V square over the R comes down and you have here GR. So guys, can't we find the alpha value easily now? So we know V is 1000 over 9 and it should be square. G value is 9.8. Radius, you can use the full value you got previous, 3536.776513. And then you can give the final answer correct to 3SF or 2SF. So let's get the value of alpha. All right, so the alpha value is tan inverse of this. So when you take tan inverse, it's going to be 19.6 degree. This is correct to 3SF. If you take it correct to 2SF, it should be 20 degrees. Okay, so depending on your accuracy, you can give 3SF or 2SF. So I chose 3SF and this is my answer. Okay, so now what you need to do is, this is one possible value of alpha. So now what's the next thing to do? The next thing to do is that you do this exact same procedure, but now using an angle theta as using angle theta as 315. Do the same thing, use theta as 315 and you will get a different radius. For this different radius, find the different alpha. All right, guys. So the other direction when theta is 315, so angle over 316 2 pi r is equal. That's the distance the plane travels equals to the speed multiplied by time. You can see it's the same time, right? So because we don't know the direction, it's the same time. So because the time is 25 seconds, I mean, you can see when you make radius a subject, guys, over here, I hope you guys can see The radius is now 505 point, you have some 25. So basically the radius is lower. So over here, I think my diagram might mislead you into thinking that the plane, actually you can see if it is going through the larger angle, you are traveling at, the plane is traveling at a quite smaller radius, because previously it traveled at a radius of 3536, because it had the 25 seconds to only turn through an angle of 45 degree. But now in the same 25 seconds, it's turning through an angle of 315 degrees. So because of that, I think it makes sense, right? You guys should realize that in this case, it's actually turning through, the circular path is actually having a smaller radius. Okay, so basically if you are going from here to here and the blue color path, they are not actually on the same circle. Okay, so the circular paths are actually different. So in this case, the center would be for the anti-clockwise motion, for the anti-clockwise motion, the plane would have to have a smaller radius. Okay, but if you were going in the other direction, if you were for the clockwise direction, the plane would have to go according to my diagram. Okay, according to my diagram, the clockwise direction, the plane needs to have a smaller radius, but anti-clockwise, it can go at a larger radius, because it only has to turn through a small angle. All right, guys, I hope you guys can understand. This was just to clarify what's happening over here, but I hope you understand that the direction, according to the direction, the radius is actually changing here. Okay. All right, so now let's go to find the alpha value. All right, so after getting the radius, the remaining part is exactly the same as the previous step. So you take vertical equilibrium and you take the horizontal, you take F equal ma towards center. You divide the two equations and you can see we get the same equation as before. Tan alpha is equal to V square over GR. It's the same story, but now the only difference is the radius is changing. So because the radius is changing, the angle alpha is changing. So the angle that the plane needs to bank to be horizontal when you're traveling along the other part, it's 68.1 degrees. So that's a steeper bank. Okay. All right. So I hope that this question is, clear with everyone. All right, guys. So part B, they say without further calculation, state how your answers will change if the aircraft wishes to complete its turn in a shorter time. So if it wants to complete the turn in a shorter time, guys, what do we need to do? I think you guys can see if you want to make the time shorter. Okay, if you want to make this take a lower time, I think you guys can see we can the time and distance are kind of like directly proportional. So you can see distance in the sense the radius, right? I think you'll have to understand it's the radius. So if you want to complete the turn in a shorter time, you'll have to probably decrease the radius. So it makes sense, right? So you can write down to turn the aircraft in a shorter time, we need to decrease the radius of the circular arc. So guys, when you decrease the circular arc, the radius of the circular arc, what happens to the banking angle? I think you guys saw from what we did in part A, the part A in 45-degree angle, the radius 3536, and for radius 505, the banking angle, there was a significant difference, right? So for the larger radius, the banking angle was smaller, while for the shorter radius, the banking angle is larger. So over here, all you have to do is to tie up all those things together and say it in a statement. Okay, so if you want to get a, if you want to complete the turn in the shorter time, the radius needs to decrease. So if the radius decreases, the banking angle must increase, right? You understand that the angle alpha must increase. All right. Okay. So I hope everyone is clear with this question now.